So in this worksheet, we're going to do some problems with dot products, generally just sort of basic things getting used to dot products and how to calculate them. We'll start off here, problem 1. We've just got a dot product of the vector -2, 4, 1, dotted with the vector 0, -3, 2. Okay, so dot product, we're going to dot two vectors. That should give us a scalar, that is a non-vector, sort of just a number as a result. And the formula for a dot product here is what we get is we should get the first coordinate of the first vector multiplied by the first coordinate of the second vector, and then we add up the second coordinate of the first vector multiplied by the second coordinate of the second vector, and then we add up the product of the third coordinates, the 1 and then the 2 there. Really, that's all we need to do, except we need to simplify this yet. -2 times 0 is 0. 4 times -3 is -12. 1 times 2 is 2. We add this up, and the dot product is -10. There's our dot product of two vectors. Pretty standard computation there. Let's do another one. Let's see if we've got 4, 3, 1, and -4, -3, 1. This is just going to be 4 times -4. Plus 3, second component, times second component, which is a -3, plus 1 times -1, product of the third component of each of the vectors. And what we get here, let's see, this is -16 equals -16 minus 9 minus 1. -9 minus 1 is -10. The -16, that should give us an answer of -26. All right, next one. This one's a little different here. We've got two vectors dotted, but we also have this 7 out here that's a scalar. There's a couple ways we can do this. One way is we can multiply the scalar through into this dot product here, or the scalar through multiplied into the first vector, distribute that 7. What that's going to look like is when you multiply the 7 through, you'll get 14, -7, 21, dotted with 0, 5, 1. You just distribute that 7 through here. And then what you get is 14 times 0 plus the -7 times 5 plus 21 times 1. And what that gives you is, let's see, 0 minus 35 plus 21. That gives you a -14. So that's one method here. Another method is you can actually say that this original expression is going to be 7 times. You can do the dot product first. So what you'll get is 2, -1, 3, dotted with 0, 5, 1. So it's going to give you 7 times 2 times 0 plus the -1 here times the 5 plus the 3 times the 1. So that's going to give you 7 times 0 minus 5 plus 3. It'll give you 7 times -2. What you'll get is -14. So either of these methods work just fine here. In fact, you also could have taken the 7 and distributed that times the 0, 5, 1 vector. It feels a little bit odd to me to do that, but you could as well. Okay, next question. Now we've got three things again. We have 3 vectors now, and they're all dotted together. So what's going to happen here, this actually isn't going to work out here if we interpret these dots, at least as dot products and not as multiplication here. The issue is, well, if you take the dot product of the first two and you dot those, that's going to give you some kind of scalar, and then you have a scalar dotted with this vector here. Now that would give you a vector here, so that would work out just fine. So that you have scalar dot vector. If you interpret this dot as a multiplication here instead of as a dot product, so you take a scalar multiplied by a vector, that would work out. The problem with this, let's just work this out here, is you then get this first dot product is 2 times -1 is -2. -1 times 3 gives you a -3. 4 times 2 gives you a +8. And then we're multiplied by 5, 1, -3. 3. Let's see, negative 2 minus 3 is negative 5, plus 8, that's 3, times 5, 1, negative 3. That's going to be 15, 3, negative 9. So that works out fine. But if you had instead decided to do this dot product first here, what you would get is 2, negative 1, 4. And then we're going to interpret this first dot now as a multiplication, sort of a vector times a scalar. And the second dot as a dot product. So we have certain difficulties here where we're reusing notation to mean different things. But then that dot product is going to be negative 1 times 5, that's negative 5. 3 times 1 is 3. 2 times negative 3 is negative 6. So we get the vector 2, negative 1, 4. Multiplied by, let's see, negative 5 minus 6 is negative 11, plus 3 is negative 8. And that gives you, if you distribute through this negative 8, negative 16, negative 8 times negative 1 is positive 8, negative 8 times 4 is negative 32. And you'll note here that we got two different answers here. So this does not work. So really our answer here is that this original expression here, this is just sort of not well defined. Does not work out, if we're going to say that here. So we have three vectors. We really can't dot them all together because the first dot product gives us a scalar, and then we can't really do scalar dot vector. Now, it's possible, here we've got the same vectors here, but I put these parentheses here. And so when you do that, we don't have this other dot. This is going to mean dot the first two vectors. That'll give you a scalar, and then what you'll get is scalar times the vector, and you'll just multiply it through. So that is really the calculation in green up here that we just did. And so here our answer really is going to be the 15, 3, negative 9 here. Oh. On to our next problem. So a new technique with vectors. One of the nice things we can do with dot products is we can find the angle between two vectors. So the formula here, the general formula, is that if you do A dot B, this is going to give you the magnitude of A multiplied by the magnitude of B. So this is now not a dot product, but these are scalars, so it's scalar multiplication, multiplied by cosine of theta, where the idea here is theta is the angle between A and B. So we have A and B, A, B, and then we have theta as that angle in there. So we have a connection between the angle and the dot products. You may see this rewritten as cosine theta equals A dot B over the magnitude of A times the magnitude of B, or something like that. I suppose you could do an arc cosine here as well. Okay, so what we're going to get here is this setup. Let's see, A dot B. First of all, let's just write it out. A dot B is 3 times 2, that's 6, plus 5 times 4, that's 20. A dot B is 26. Magnitude of A, that's going to be the square root of the 3 squared plus the 5 squared. Square root of 9 plus 25. Square root of 34. And then the magnitude of B is going to be the square root of 2 squared plus 4 squared. Square root of 4 plus 16. That's square root of 20, which you could write as 2 square roots of 5. 20 is 5 times 4, and then the square root of 4 is 2. So we get all our components we need. And so what you're going to get here is theta, in the end, is going to be an inverse cosine or arc cosine of, so we're going to take inverse cosine on both sides. We get A dot B, that's 26, over magnitude of A, square root of 34. Magnitude of B is 2 square roots of 5. So our angle here is cosine inverse. The 26 and the 2 cancel to give us a 13 over 5 times 34 is 170. So let's make that a little bit nicer here. About 13 over square root of 170. There. So this could be an acceptable answer. Sometimes it's nice to write that as an approximation for decimals. I'm going to bring up my calculator here. And what I'm going to do is just an inverse cosine of 13 divided by the square root of 170. And what you get here, apparently this is like, whoops, didn't pay attention. What it was like 0.077. How about 0.077 radians? So a pretty small angle. These two are pointed. I mean, it sort of makes sense. They're kind of pointed in the same direction. If you tried to graph this here quickly, you could do 1, 2, 3. Let's stick that out. 4, 5. 1, 2, 3, 4. Whoops. Let's start over here. Make this a little bit nicer. Let's just a chart here. Okay, so I get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so I get a 0.24, something like that. So that's going to be B. A is going to go to 3, 5, somewhere up here. And you can see on sort of my crude drawing, these look like they're almost in the same direction anyway. They're not multiples of each other, but we have a very small angle here between them, so that seems plausible. Okay. Next question. Same setup. We have two vectors. We're going to use our formula from above, so we have to do A dot B. First setup here, we get 1 times 0, that's 3. And then the 0 times -2, that gives us a plus 0. So the dot product is just 3. Then the magnitude of A, well, this is going to be the square root of 1 squared plus 0 squared. Note when you have the 0, this is just going to give us square root of 1, just 1. So really just, this is a vector of length 1 pointing in the x direction. B's magnitude is square root of 3 squared plus -2 squared. So that's going to be square root of 9 plus 4, square root of 13 here. And so theta should be inverse cosine. Formula was A dot B, that's 3, over the magnitude of A, that's 1, times the magnitude of B, that's 13. So maybe you write this as inverse cosine of 3 over the square root of 13. So that's your answer. If you want an approximate answer, so I don't really have any idea what inverse cosine 3 over square root of 13 is. We could go calculate that. So I could do a second inverse cosine 3 divided by square root of 13, close the square root, close the inverse cosine, and I get 0.588, something like that, as an approximation. You could figure out if that really makes sense or not. Now, I got think about this in terms of pi, so let's go back to pi. How many pi is this? So if you divided that by pi, actually, well, we'll do it this way. Divide by pi, this gives you about 0.187 pi, so it's about pi over 6, maybe, would be our answer. And so if we go back, does that seem like it makes sense here? Well, what we have, let's go back to a graph. Let's do this over here. We have 1, 2, 3, 1, 2. So 1, 2, 3, 1, 2, we're right there. And so we've got one vector there. There's B, which I like to draw first. And then A is actually up here. And so you have this angle here. I could buy that that's like pi over 6-ish. It seems plausible. And you don't need to do this check, but sometimes it just feels a little better to have a sense of that. Okay. And another one. Same setup. A dot B is -2 times 3, -6. 1 plus 6, that's 6. That gives us 0. Okay, so this right away I know is a special case because my formula, if you look at it, was theta is going to be inverse cosine of A dot B over magnitude A times magnitude of B. Without calculating magnitude A, magnitude B, we already know that we're going to get 0 over something here, well, magnitude A times magnitude B, but that's just going to be 0. So we're going to end up with cosine inverse of 0, which is going to be, let's see, what gives us a cosine of 0? That's going to be pi over 2, which would be sort of 90 degrees here. Okay, now, does that make sense here? Well, if you graph this, what you're going to get, let's see what happens. Here's -1, -2, 1, 2, 3, 4, 5, well, 6. So we got to go out at least 1, 2, 3 here. So we have -2, 1. Maybe do this in purple so it shows up a little better. So this is the 1 vector. It's actually A. And then B can be something like that. Now this pi over 2, that's 90 degrees. That means we have a right angle here as you go along. And that seems plausible with my rough sketch here, that could be a right angle. And so there's a common sort of, I guess, fact that we want to know is that when you dot two vectors and you get 0, that means the two vectors are perpendicular, or sometimes you hear the word orthogonal, or they're at a right angle to each other. Whoops. Let's start chart here. Okay. So in the end, dot product is 0 means the angle is pi over 2. Next problem. Now we've got vectors in three-dimensional space. It's going to be harder to draw, which I'm probably not even going to bother with, but we can still find the angle between these. You could actually use this formula to find the angle between two vectors in R5. The dot product be defined the same. You just take the sum of the products of the corresponding coordinates. Everything will work out the same. But here what we get is A dot B. I get 3 times 2 is 6. 4 times -3 gives me -12. -1 times -2 is a +2. Add that up. 6 plus 2 is 8. Minus 12 is -4. And I need a magnitude of A. It's going to be square root of 3 squared plus 4 squared plus the -1 squared. So this is square root of 9 plus 16 plus 1. That's square root of 26. And then the magnitude of B is the square root of 2 squared plus -3 squared plus -2 squared. So it's a square root of 4 plus 9 plus 4. It's a square root of 17. And so our theta is inverse cosine of A dot B is -4 over magnitude A is square root 26, magnitude B is square root 17. You could, I guess, multiply 26 by 17 and write that down as square root. I'm fine with this here. If I wanted an approximation in radians, here, I could do a second cosine inverse -4 divided by the square root of 26. And then I have to divide by the square root of 17 because I did not put parentheses on that bottom here. And I get this to be something like, whoops, 1.76, I think it was. 1.762 perhaps. There as an approximation. And that's in radians. Might be a little bit easier in degrees to think about that. Okay. Last one here. We're going to do A dot B. Something special is going to happen here. I can see it right away. We'll talk about it at the end. We get 3, 2, 1. Whoops. Well, we would, but let's just save space by multiplying this out. 3 times 9 is 27. 2 times 6 is 12. 1 times 3 is 3. Add that up. That gives me 42. Magnitude of A is square root of 3 squared plus 2 squared plus 1 squared. Square root of 9 plus 4 plus 1. That's square root of 14. Magnitude of B That is square root of 9 squared plus 6 squared plus 3 squared. So that is square root of 81 plus 36 plus 9. 9 plus 81 is 90, plus 36 is square root 126. Okay, and so what we get is theta is cosine inverse of a dot b is 42, and then I do the square root of 14 times square root of 126 here. Now, this, is kind of ugly, and maybe I should worry, can I simplify this? In particular, there's at least a factor of 2 that can come out of the square root, because I have a 14 is even and a 126 is even. So what I'm going to do here, so cosine inverse, I can pull out that 2, so I get 42 over 2, and square root of 7, see 126 divided by 2, that's a 63. Whoops, don't want to angle bracket, I want a parenthesis. So this is cosine inverse of 42 over 2, that's 21. And then the 63 is going to be 7 times 9, so I'm going to get a 7, and I'm left with square root of 9, that's actually going to give me a 3. This whole thing is then going to be cosine inverse of 21 over 21, that's 1. If I look out, that gives my answer of the angle is 0. Radians or degrees. So that's our answer. Now, I said at the beginning of this problem here, there's something I noticed that sort of meant I could shortcut this right away here. And what this means, angle is 0, that means these two vectors are pointing in the same direction. So what I noticed here is that if you take the vector 3, 2, 1, that is A, and you multiply that by 3 here, what you get is 3 times 3 is 9, 3 times 2 is 6, 3 times 1 is 3, you get this vector 9, 6, 3. So the one vector is a multiple of the other. That means they're pointing in the same direction. That is, the angle between them is 0. There. So if you notice that right away, you can avoid all this computation. You don't have to deal with this 14 times 126 business here. Okay, 2 more. So very similar type of question, although it's going to look different. Split up. So we're going to find the angle between the lines y equals 3x minus 4 and y equals 2x plus 1. So I've got 2 lines here. When I talk about the angle between lines, all I really care about is the slopes here. And if I look at this, when you have y equals 3x minus 4, the slope is 3. Now, and if we take y equals 2x plus 1, here the slope is 2. So you learned, presumably before, that the slope sort of gives you a slant of the line. If you think about it another way, that's really a direction or a vector here. Now, when you have this m, I tend to think of it as change in y over change in x here. Note here that means that when we have m equals 3, we could say that it's sort of like, well, how about this? That the change in y is 3 and the change in x is 1. Well, that really gives us a vector. Let's call this vector 1 of, well, x changes by 1, y changes by 3. So what we're saying here, just draw this out quick, is that if you have a line whose slope is 3, let's see, we're going down 1, 2, 3, 4, right there, 1, right there. Let's maybe draw that in purple. So you have a line whose slope is 3, looks something like this. So we think of slope as 3 means I move over 1 in x, I go up 3 in y. So that's one way to think about it. Well, it turns out, let's maybe do this color here, brighter green, that this vector, that's the vector 1, 3. So in some sense, that slope is 3. It's the same thing as saying that we're in the direction of the vector 1, 3. Just a different encoding. So a vector in the direction of the first line is 1, 3. Can do the same thing for the second line with slope 2. So when m equals 2, we get change in y is 2, change in x is 1, and this leads to a second vector for the second line of 1, 2. So now we have vector in the direction of each line, and so we can find the angle between the vectors will give us the angle between the lines. So what we're going to do, same thing we were doing on the previous page, we do v1 dot v2. That's 1 times 1 is 1, 2 times 3 is 6, that's 7. Magnitude of v1 is square root 1 squared plus 3 squared, square root 1 plus 9, that's square root of 10. Magnitude of v2 is the square root of 1 squared plus 2 squared, that's square root of 1 plus 4, that's square root of 5. And so we get a theta of inverse cosine, our dot product is 7, and then we multiply the magnitudes, that's our square root 10 times square root 5. Now note, 10 times 5 is 50, there's a factor of 5, or really 25 there, and so you could turn this into cosine inverse 7, 5, square root of 2, 7 over 5 square root of 2. Maybe it looks a little bit nicer here, not strictly necessary. So in some sense, that's your angle. It might be nicer to do a measurement. Let's try this one in degrees just for the sake of here. So I can go to mode, go to degree, or however you do that in your technology. And then we can just do a cosine inverse here. 7 divided by, and the last one I didn't put parentheses here, so I will, 5 times the square root of 2. I have to put the multiplication. And I get an answer of 8.13 maybe. So this is 8.13. Note that's in degrees, not radians. So maybe you want to put an answer like that. If you want an answer in degrees, here you had 2 lines from equations, and we got an answer in terms of the number of degrees between the lines. Here using the slopes, turning them into vectors, and then using dot product things. Okay, one more like this here. So find the angle between the lines 3x minus y equals 5 and 2x plus y equals 7. Here our slopes are a little bit trickier to find. One thing you could do is I could just say v1, I don't really care what the slope is, but if I increase x by 1, that increases my left-hand side by 3, so I'm going to have to increase my right, or the y by 3 as well. So that'll be increased by 3, increasing y by 3 decreases the left-hand side by 3, and those will cancel out, and I'll still get 5. You could also go to the slope. Slope will be 3 and do the same thing as before. v2 can do the same thing here, where if I increase x by 1, then y, let's see, if x goes up by 1, the left-hand side goes up by 2 because it's 2 times the 1. So I need to decrease by 2, means I need to sort of add negative to the 1. So those are my 2 vectors. And now we just find the angle between them. So I'm going to do v1 dot v2 here. What I'm going to get is 1 plus 3 times negative 3 is negative 6. That's a negative 5. Magnitude of v1 is square root of 1 squared plus 3 squared. So it's going to be square root of 1 plus 9, square root of 10. Magnitude of v2 is going to be the square root of 1 squared plus negative 2 squared. So it's going to be the square root of 1 plus 4. Again, the square root of 5. We've got some stray marks over there. And so then our theta is going to be the inverse cosine of, let's see, we have negative 5 over square root of 10 times square root of 5. And here it's going to pay to actually do the simplification. So I get negative 5 over 5 square roots of 2, which is negative 1 over the square root of 2. The 5's cancel. You might be familiar with this setup, depending on how you've done things in the past. You could multiply the top and bottom by square root of 2, and this is negative square root 2 over square root 2. And so that's going to give you an angle of, that's going to be 3 pi over 4 here in radians, or you could think of that as really 135 degrees if you'd like to do it that way. Okay, that ends our worksheet for the first part for dot products.